While you're taking a look at the announcements, let me hand out the notes for today.
Can we turn our homework today?
Certainly. I'd be delighted to take it. All right. So we're not going to have a live class on Friday. I considered whether it would be feasible, content-wise, how much of a compromise that'd be, and I think between the pencast and so forth, we can probably get away with it. So you can, I know you're not going on vacation. It's probably that there's an engineering field trip of some sort that all of you are anxious to attend on Friday, because I've had a few people mention that they aren't going to be around. So that's the only thing I can figure is that it's an engineering field trip. Maybe it's a personally guided engineering field trip. So homework on Friday, you can give it to me now, or slide it under my office door by 1 o'clock on Friday, or just email it to me by that deadline. So any scheduling or announcement questions? All right. Well, last time we looked at the specific energy diagram shown on the left side of the screen there. And the specific energy diagram, remember, is for some certain flow rate Q and for a fixed channel geometry and a certain n value that doesn't change. But what does change is we can have a variety of different flow depths for the same flow rate by changing the slope. And so we could have a steep slope that gives a shallow depth and fast velocity, or we could have a mild slope that gives a deep depth and a slow velocity. And for any certain amount of specific energy, there's two possible flow depths, and those alternate depths represent the same amount of specific energy, but just simply one of them is a subcritical route, the other is a supercritical route. And then, of course, the exception to that is the point of minimum specific energy, where there's only one possible flow depth, and that's the critical flow depth, Y sub C. So this is just a review of last time, and the way that we get different specific energies for different flow depths, for steady uniform flow, how do differing depths yield different specific energies. It's because if you have a faster moving velocity, there's going to be more kinetic energy there, and so that's why it has additional specific energy.
I have a question about the specific energy equation.
Sure.
Is there a way for Excel or anything to put it in and solve for the minimum value that would make varying Y?
Yes. For varying Y?
Varying Y values?
Okay. So let's say we've got the specific energy diagram, Y plus Q squared over 2G A squared. For some rectangular channel B width, Y depth. Yes. So your question is, can you find the minimum?
The minimum E by changing the Y value.
Minimum E, yes.
Like a critical.
Mm-hmm. So in Solver, there is the option to not only solve for a known value, but also you can minimize or maximize things. So data, Solver, so max, min, or a certain known value. So if you wanted to minimize the specific energy, you can write the E equation in terms of Y, and it will play around with the Y until it finds this minimum specific energy. Okay, so this graph, the specific energy diagram, is one way of visualizing the energy situation for fixed flow rate, roughness value, and channel width. Now, this is a little bit different. Along this curve, everywhere on this line, the flow has the same amount of specific energy. On the x-axis is flow rate, and on the y-axis is depth. And so What this is illustrating is that you can have some of the specific energy be in the form of depth, and then if we're at this point right here, only a certain amount of the specific energy is depth. The rest of it would be kinetic energy. Or here at the top, this would be where almost all of the specific energy is as flow depth and very little is as kinetic energy. So last time what we talked about for this minimum point, what that represented is the least amount of specific energy associated with a certain flow rate. Now here again, this is showing the minimum amount of the critical point, y sub c, which we associated with the minimum amount of specific energy for a certain flow rate. This is a graph of everywhere has the same amount of energy, and so it's the maximum flow rate for that certain amount of specific energy. So it's just a different way of saying the same thing. On the previous graph, what we were seeing is the minimum specific energy for a certain discharge. What this illustrates is the maximum discharge, the biggest Q, associated with a certain specific energy, and everywhere on that curve has the same energy level. And the critical depth is that most efficient point where you can get the most flow for a certain amount of specific energy. And these are really interchangeable. It's not either or. These mean the same thing. All right. Now this E naught on the y-axis, what it's showing here at the top is that you'll have zero flow rate if you just have all of the energy is depth and there's no velocity, then you'd have no flow rate. And that's what the intercept means. And so everywhere along here has the same amount of energy, and the intercept at the bottom means it's not really possible to have all of the energy be as velocity and have no depth. If you have no depth, and there again you're going to have zero flow rate. And so at the two extremes, there's no flow rate up here because there's no velocity, and down here there's no depth. And everywhere in between, it's some combination of flow depth and velocity that gives you the same constant specific energy. We won't use this graph as often as we use this one. You'll actually have to create specific energy diagrams to solve problems. I don't think that you'll ever create a constant specific energy diagram. It's more of just an illustration that makes the point of what the critical depth represents. The critical depth represents where the maximum flow rate can be achieved for the same amount of specific energy. Okay, so we've talked about very briefly why it's important to know whether conditions are supercritical and subcritical. And among the reasons why we feel like it's important to know is those conditions govern the response of water to something like a step downwards, which is illustrated on the screen here. On the screen, you can see that the water's flowing along normal conditions. Now, this Y1 is showing that before the water encountered this step, the actual flow depth was deeper than the critical depth. So what does that tell us about the flow regime? There's two possibilities. There's subcritical and there's supercritical. And on the left-hand side, before the step, we're seeing that the normal flow rate, the flow rate at the flow depth at location 1 was greater than the critical depth. And so at 1, y is greater than y sub c. And so does that mean that it's subcritical or supercritical? Subcritical. It's subcritical. Subcritical. All right, and it's hard sometimes to remember. Subcritical means essentially slow velocity. It's the root that has the slow velocity and the deep flow depth. So that if we calculated the Froude number here, what we find is that the Froude number is less than 1 at location 1. subcritical conditions, because the actual water surface is deeper than the critical depth. And so the importance of it is that after the step, the water will stay subcritical. You know, whenever you have any kind of a change, like a step down or a step up, or a channel getting wider or a channel getting narrower, what we have to understand as a starting point is before that change, what was the flow regime? And here, the flow regime is subcritical before, and so it's going to stay subcritical after. You can see that at 2, the depth is still deeper than the critical depth. And so at 1, it was subcritical, and so at 2, it will still be subcritical. We're changing how much energy there is by having this step downward. What's the new flow depth after a drop is what we're going to be trying to find. And we're going to solve that by computing the specific energy and the total energy and seeing how things have changed. And so what we're given in a problem like this is an initial depth. We'll be given a velocity so that we can characterize the conditions at once. So we can know if conditions are subcritical or supercritical. And we can create a specific energy diagram for the flow conditions. And we'll step through this just to illustrate what happens during the drop down. First of all, we would want to identify our initial flow depth. So this is line 1, which is now in red. And we go down to the energy axis, and we find our initial energy level, the initial specific energy. Because it's a step down, the specific energy increases. We're adding energy in the form of delta Z. And so we go to the right because now there's additional specific energy. When there's a step down, you add delta Z to find E2. So this is a rule you're going to have to commit to memory of how the energy is changing. A step down, E2 is the energy at 1 plus the change. And that just makes sense. You know, the water is going down, it's gaining energy. It's sort of going off a cliff in a sense, and it's picking up some specific energy because of that delta Z. And so now on the diagram, what you'll notice is that we went from our initial energy level, E1, over to E2 because of the delta Z. And so we can find out what's the new flow depth. Well, there's 2 possibilities. The flow depth could either be this flow depth here that's associated with however much specific energy we've got now, or it could be this other alternate flow depth. And so which of the 2 flow depths will it be? Well, it'll be the subcritical flow depth because we were subcritical before. And so that tells us which of those 2 flow depths we should go over to the y-axis and find the new y2. And so that's a graphical illustration of it. You step through the problem-solving process to start with some initial flow depth y1 and find the new flow depth y2 because of a drop down. Any questions about? Yeah.
I assume that y2, it looks like it's actually the elevation's higher than at y1.
It is, and you can see on the specific energy diagram why that is. You know, here was our initial y1. If you're subcritical and you have a step down, so a step down moves us to the right, it'll make the flow depth deeper as a response to that.
So would you be able to see the elevation of the water is actually a little bit higher, or is that just hiding through the?
It can be immediately visible to the naked eye. Sometimes it's subtle enough that you can't notice it. It depends really on the delta Z, how big the delta Z is, and the slope of this curve. So if it's like a 1-to-1 slope on the curve, then a delta Z of 10 centimeters would give you a water surface change of 10 centimeters. Okay, so what do you think would happen if it had been supercritical conditions at 1? Okay, it'll stay supercritical at 2, and so would the step down make the water deeper or shallower? More shallow. And if you look at the curve, you see why. Because if we were here to begin with, and we have some delta Z, then the new supercritical route would have been here. And that's going to be shallower. All right, so I guess if you'd like, you could commit a rule to memory that if you have subcritical conditions, a drop down will make the water deeper. If you have supercritical conditions, a drop down will make it shallower. But you can always just sketch a curve like this and remind yourself what the relationship is in the same step-by-step approach that we've just gone through here on screen. All right, well, let's do an illustration of this where we've got a bed drop with some actual flow data in here. We want to find what's the flow depth after the drop that's described. We have a 1.2 foot drop, an initial flow rate of 30 cubic feet per second. And actually, the flow rate doesn't change just because the flow depth is changing. And so Q1 equals Q2. And we want to find out what will be the new flow depth after the drop. All right, so first of all, we want to characterize the flow condition at 1. We want to know, is it subcritical or supercritical at 1? And so at 1, the Froude number, I'm going to use the equation Q squared times T divided by G A cubed to the 1/2 power. All right, so 30 cubic feet per second squared. The top width will be 8 feet. It's a rectangular channel. Okay. G is 32.2 feet per second squared. And 28 feet squared is the cross-sectional area. Cube that, everything to the 1/2 power. And so the Froude number is 0.101. For later. We'll talk about that. So are conditions supercritical or subcritical? Subcritical. All right, subcritical at 1. Good to know. And that's unitless, by the way. We can find the velocity at 1 is Q divided by A1. And so the velocity is 1.071 feet per second. We know the flow rate is 30. We know the cross-sectional area, so we can find the velocity. Okay, the energy at 1 is Y1 plus V1 squared divided by 2G. All right, that is 3.5 feet plus 1.071 feet per second. Square that, 2 times 32.2 feet per second squared. Okay, our total amount of energy at 1 is 4.718 feet. Okay, and so the energy at 1 is, let's go back to our slide previously. It says energy at 2 is energy at 1 plus delta Z. So the other way to write that is the energy at 1 is energy at 2 minus delta Z. Or I guess really what we're trying to find is what's going to be the new depth. But I just wanted to show you that, if E2 is E1 plus delta Z, then E1 is E2 minus delta Z.
Why is the energy at 1 on 4.718?
Are my calculations wrong? It is.
3.5.
You know what? I've already accounted for the 1.2 foot drop. So yes, thank you for noticing that. I was combining things on the page and trying to separate them here. So what did you get?
3.517.
I'm glad that you're checking the calculations. What I had done is already moved the 1.2 over, so that was an accident. Okay, so E1, 3.5178 feet is equal to E2 minus the 1.2 feet. Okay, so what that says is that E2 is 4.718 feet. So we know E2 in terms of the magnitude of it, and the components of E2, so 4.718 feet of energy. That is the depth, Y2, plus, it'll be the flow rate, 30 cubic feet per second squared, divided by 2G and A squared, 8Y2 squared. I wrote my velocity head term here in terms of velocity. Since I don't know the velocity here, I'm just going to write it in terms of Q, and then down in the denominator half of the area. All right, yeah. So that is, if we rearrange it, it'll be Y2 cubed minus 4.718 y squared plus 0.2184 is equal to 0. And we have to get the 3 roots of that. Of those roots, we know it won't be the negative root. And so how do we know which of the 2 flow depths to use? Is it going to be 0.22 feet, or is it going to be 4.7 feet as the new flow depth?
4.7.
So how do we know that it will be this depth and not the other?
Subcritical at 1.
This is the subcritical root, right? And we had subcritical at 1, subcritical at 2. So this was the supercritical root. It won't be supercritical flow, it'll be subcritical flow. And so now we have the new flow depth at 2 after the drop. It gained energy. Well, where does that energy go? Makes it deeper. If it was supercritical, what it does is that extra energy goes into extra velocity. Okay. Any questions on that example?
Dr. Wade, given like a cubic equation or like the Manning's equation we were working on previous week, would a TI-89 be acceptable like on an exam? Should we encounter something like that?
That would be fine to use a TI-89.
Okay. Yeah. Just making sure it's successful.
Yep.
Okay.
Okay, what if it's a step upward instead of a step down? All right. Assuming that we have subcritical flow at 1, the flow at 2 will stay subcritical. And so if we consider it in terms of the specific energy diagram, The energy at 1 is how much energy is available to push it up over this obstacle. You know, the step upward, there is some critical step at which it's too big of a step and the water can't make it up over the obstacle anymore. But let's say it's a relatively small step. What's going to happen is that the specific energy does change by delta Z. There will be less specific energy at 2 than there was at 1 because of the step up. But the total energy doesn't change. The total energy relative to the datum that is horizontal doesn't change. And so what this illustrates is the difference between total energy and specific energy. Specific energy is relative to the channel bottom. And so there's less energy relative to the channel bottom at 2 because the channel bottom is higher than it was at 1. Okay, so let's just look at the specific energy diagram because it's really what we can use to make sense of things. Initially, we had a depth of Y1, subcritical conditions. Okay, so there Y1 gives us a certain energy level, E1. Because it's a step up, we're losing energy, which means we move to the left on the x-axis to energy level 2. There can be 2 different routes. There could be a supercritical route as the new flow depth or a subcritical route as the new flow depth. Well, because it was subcritical conditions at 1, it will be subcritical conditions at 2, and so then that gives us the new depth Y2, and that step up made it so that it will be more shallow at 2 than it was initially.
Wait,
Mm-hmm.
is there ever a situation where it can go from subcritical to supercritical if it's like really close to that critical point with the up or down step? Or is it always gonna stay?
So you're asking if it can go from subcritical to supercritical.
By just adding a step or a drop?
The only thing that will allow a transition from subcritical to supercritical is if the water is approaching a drop-off. And so it's speeding up because it's going to go over the side of the cliff, not because of the step up. A step down, I suppose you could consider this a step down if it's flowing over the side of the cliff.
I was thinking because if you subtract your delta Z, you were really close to that. It's,
Yeah.
that wouldn't matter.
There is a, you know, as you get closer and closer to the critical depth and the minimum specific energy, then there's going to be less of a change. Yeah. All right, so in this example of a step up subcritical flow, the new depth is less deep. The flow depth at 2 is less deep because there's less specific energy. If it's supercritical conditions, then what happens with the step up is, if we just consider things on the specific energy diagram, we start at Y1, go over. The step up means that we're losing specific energy. We get to the left on the diagram, go back up, and it's going to be deeper. Right? So the depth at 2 after the step up will be deeper than the depth at 1. And what you'll notice on the diagram here is it's showing that it's closer to the critical depth. And so at 1, there was kind of a big gap here. The flow depth is further from the critical depth, but then at 2, there's less of a distance between the actual flow depth and the critical flow depth. And so what that's showing is that you're closer to the critical depth after you've gone through that step up. All right. I'd like you to give this a try. Find out what will be the flow depth after a step. This is a step up, and we have, I'm not going to tell you if we've got supercritical conditions or subcritical conditions. I'd like you to just solve this one, although I will give you one simplifying hint on this example as you get things started, and that's to remind you that you can calculate the critical depth for a rectangular channel. Remember that y sub c is q squared divided by g to the 1/3 power. All right. So It's the same process as it was in the other example, where you want to determine whether flow is supercritical or subcritical, find the energy at 1, and then find the energy at 2. All right, so on this example, we find the critical depth is 2.7 feet, and since that's less than the 5 feet of flow depth at 1, that means the conditions at 1 are subcritical, and that tells us that conditions after the step upward should be subcritical as well. We find the specific energy at 1 is 5.388 feet, and accounting for the step up at 0.5 feet, that means that there's going to be 4.888 feet of specific energy available at 2. And that specific energy is going to be in the depth, as the depth term, and this is the velocity head term, when we substitute in the flow rate, the cross-sectional area, and so forth. So we can rearrange and get our cubic equation here. Y2 cubed minus 4.888 y2 squared plus 9.705 is equal to 0. And the roots of that are negative 1.26, 1.762, and 4.383. And of those, it's going to be the subcritical root. And so it'll be 4.383 feet after the step up.
Does it decrease the subcritical step up?
And it did. The flow depth initially was 5 feet.
So how do you know it's not the 1.7, just because that's too big of a jump?
Because this is of the two, this would be if conditions were supercritical, and this is the one if it was sub. So it's not the value itself relative to the initial one being too big of a step or too small of a step, but our critical depth, 2.7 feet, is the dividing line. So
those are just the subcritical and supercritical roots. That's how you look at that. So no
Yeah.
matter what, the bigger one's the subcritical.
right. It's either no matter what, the bigger one's subcritical, or we can actually compare them to what we know is the critical depth. All right, well, that's it for, until spring break. Of course, you'll hear my voice on the recorded lecture and have a quiz covering the recorded lecture after spring break to make sure that you have the incentive to watch it. But